last class, which is unlikely because most of you did not attend. But yeah, let us go ahead and start. Can you see the whiteboard?
Yes, sir.
Yes, sir.
Oh, what is it? Why is it configuring? Sorry. New. अरे क्या होने लगा? कौन तो ट्रबल करेगा? अरे got it. Let us change it again. Every time it keeps changing. Okay, it doesn't really matter. 1 second, let me sort of get out of it and see if I can type a whiteboard again and get back to our old model. Again and again. Maybe I should go to the old one. No, somehow. Anyway, let's see. Oh, it's very fat. ये थोड़ा मुश्किल हो गया. I think I'll need some more time. I need to get back to the old whiteboard, which has a thinner pencil structure. Is this something which I taught? No?
No, sir, not that.
2020, 2020, 2020.
On new whiteboard, and then we can.
New whiteboard will again create the problem of my pen size. Okay, it doesn't really matter.
Pen size can be changed just clicking on that.
No, it is not changing the size.
Yeah, size can be changed from there.
Yeah, that is it. That is the thinnest. Yeah. Yeah, this is much better. Thank you. Yeah, so essentially we were talking about multiple equilibria, and I think you all were familiar, and you all got the argument that I was trying to make, that multiple. Oh my goodness, it is so fine that it is not. And maybe I should make it a bit thicker. Yeah, maybe it is better. Yeah. Anyway, so essentially, you remember what I did, right? I said I found out R, the ratio of bound to unbound, which was A bound. Responding upon E naught. E naught is not actually E naught, but the number of sites actually. So E naught in that sense, A bound was, if you remember, what was it? EA plus 2EA2 and so on and so forth, right? Plus, this has become a very bad whiteboard. 3EA3 and so on and so forth till NEAN. And the total E naught was E plus EA plus and so on and so forth, right? Plus EA2 plus. And what I did very clearly was that I sort of then tried to first then convert it to microscopic binding constants by this essential argument that Ki, the macroscopic Ki, was what? Remember E A, and this is I minus 1, right? Into A upon EAI, right? So EAI is so essentially the argument being I'm sort of revising here, EAI plus A is, sorry, I minus 1 is EAI with a macroscopic binding constant of capital Ki. Remember that the macroscopic binding constant is a function of the microscopic binding constants, and that, remember, was the binomial equation that I was talking about. And so R then obviously using this kind of formulation became equal to, can you tell me what it was? A by K, K1 plus 2A square. I hope you realize this. I remember this. K1, K2 plus, 3A cube,
3a cube upon
K1,
K1,
K2,
K2, K3.
K2, K3, and so on and so forth, and so on, K1, K2, K3, and the bottom one was simply 1 plus A1, again, A1, A by K1, oh, sorry, I'm so sorry, plus 8A square upon K1, K2, this pen is not good, plus so on and so forth, and then I reduce this expression to, so I'm sort of revising here very quickly. Then I reduce this expression to the summation equation that I wrote. And I also told you about the fact that this is essentially a statistical or the number of options. It's like a permutation combination equation issue with KIs, right? So first of all, I wrote R equal to, let's see if this is better. This event pattern. No, I don't know the arrow. R is equal to, why is it arrow? Arrow हटाना है ना.
Click on this circle below.
Yeah.
There is 2 arrow and there, yeah, that circle.
Yes.
That,
No,
yes.
yeah, that's it. Yeah. So then what was R? So R was essentially equal to, फिर R नहीं आया, ठीक है, summation I to N, I mean, what was it? And I hope you remember, AI, of course, A raised to I, not AI, divided by, and pi, the multiplication, Ki, Kj, let me call it Kj, J equal to 1 to I. Right? And then divided by this same thing, 1 plus summation I is equal to 1 to
I
N.
equal to 1
This
to
is what we
N.
did. Yeah, and you remember A raised to I upon A raised to I upon pi. The same thing, right? Kj. Right? And then what I did was, so essentially, if you see this argument, that then what we did was we started using the multiple equilibria where we said that Ki was essentially a function. Now this is where, so the Adair model stops here. The Adair model stops here, and we say that the Adair model for 2 models, 3 models, you can write it, because there is no way that these K values, these Ks have to be, are independent, and they have to be determined experimentally. And these are the macroscopic parameter binding constants for EAI plus A on the IS step. But if we assume that they are only statistically or derived from the number of permutation and combination steps, and each of these KDs, the dissociation constants, which are the microscopic dissociation constants, are the same, if we say that the microscopic dissociation constants are what are leading to these things, and the microscopic dissociation constants are all exactly equal, then of course we can make all kinds of simplifications. So this is the Adair model, but which is complicated, and we could simplify it by saying that all macroscopic dissociation constants are equal, and the change or the reason why Ki's are different is to do with the fact that each of these Ki's has a different set of steps leading to Ki. Remember that argument? Right? And so we could very easily write that basic expression that I was trying to tell you, that each of these was actually, because NCI was the number of ways in which you could talk about the previous step, and NCI minus 1 was the number of steps that was possible for this. Therefore, the ratio of this KIs was equal to, I hope you remember, N minus I plus 1, of course, right, upon I, right?
Yes,
And
sir.
so what? हाँ, ये लास्ट क्लास में डिराइव किया था, आप लोगों को याद है? And so therefore we can substitute this expression here R as R is equal to, come on now, let's have some from you people, from you guys. I summation, of course, first of all, and then I pi, and then n minus 1 plus I, and n minus 1, n minus I plus 1 कर देते हैं, चलो. Okay, divided by I, right? And we have AI, a raised to pi, and now we can have KD. Is that all right? KD raised to pi. I mean, actually, the whole thing raised to pi. Is that all right? And the bottom expression was 1 plus summation, and then pi again, and then again the same thing, n minus I, plus 1 upon I, and again a by, can you make out? KD raised to pi. So see, instead of K1, K2, K3, K4, I can write them as this multiplications of this, because each of these, so K1, K2, K3, for example, I hope you realize K1, K2, K3 till Kn, and each of these is related to this is related to this, this is related to this, this is related to this. So each of these is, and each of these ratios are n minus I plus 1 upon I, right? So I can simply sort of get them all down to the dissociation constant level and bring it and write it like this. Is that all right? Hello?
Yes.
Oh, you didn't attend. Yeah. So
Okay.
now look at this expression here. And remember your binomial theorem. And if you remember your binomial theorem, essentially I'm trying to derive something very trivial, but you know, I'm trying to tell you that this is consistent. And do you remember your 1 plus x, this sort of n, 1 plus x is sort of n expansion? And do you see that this here is 1 plus x expansion? Or do I need to show you? Think about it. These are the binomial coefficients. Right? So this term here, this whole thing here is 1 plus x sort of n. And so actually the denominator becomes 1 plus a by kd raised to n. And the numerator would require a little bit of clever tricks. It is actually, I mean, I'm not going to do this. I wanted to go back and think about it. As I said, I will move this a plus a by kd into 1 plus a by kd raised to n minus 1. Do you understand why? There's an I here, so that is why. Sorry, not this I. Where was this? Here. This is the one. N a by kd, and then this is there. So this one here is what you get. This is what you get. Which, as you notice, would reduce to the simple, if kd's were all equal, that is what we basically assume, would reduce to the same expression for, I hope you realize that this expression becomes very simple. What does it become? What does this expression become? Na by kd upon 1 plus a by kd, right? Which of course is equal to what? Na upon kd plus a, right? So you see n sides, so it is Na kd by a. the number of binding constants. So if obviously if they were all equal, it would get to the same, back to the same hyperbolic form with s upon ks plus s being replaced by ns ks by s, where because there are now n binding sites. Right. So this would be the simple hyperbolic expression that we are talking about. But Adair model then does not assume these things. It says macroscopic binding parameters have to be separate. If they were all determined by the microscopic binding parameters and we use the standard binomial logic of the number of permutations leading from K1 to K2, K2 to K3, K3 to K4, and so on and so forth, then we could bring this term in here. And then if we made the further assumption that all KDs were equal, then we could simply take the binomial expansion and simplify this whole complicated expression, this whole complex expression into something rather simple. So this would be the simple expression. Let me sort of write it in this color, right? So that is the whole idea. So this is the general equilibrium model. The Adair model stops one step before that by saying this simplification is no longer allowed. And then there are obviously all kinds of models that work on top of this, which is for example, I could think of clever modification of this basic mathematics, which is that I can say that each of these ki's, for example, each of these ki's is a multiple of the other. So one of the things which, for example, the great Pauling, I have a word of his name, I'm sure, Pauling proposed, the Pauling model as it is called, he proposed that I will simply say that each, there is an interaction factor alpha. So I hope you remember that for the four model system, you remember your equations. K1 was equal to KD by 4.
Yes, sir.
K2 was equal to 2 KD. Sorry, 2 KD. क्या था? 2 by 3 KD, right?
Yes, sir. 2 by 3 KD.
Oh, but you see the n plus n minus I plus 1 upon I करिए ना और कुछ नहीं. ठीक है ना? 2 by 3 for n is equal to 4. 2 by 3 KD. K3 क्या है?
3 by 2 KD.
3 by 2 KD.